is we've made some nitrogen dioxide gas by reacting nitric acid with copper filings. We used concentrated nitric acid so that we had a high number of particles per mil, so a higher rate of reaction or successful collisions. And we used copper filings so that we had a large surface area to volume ratio. So a lot of the particles available, again, increase the rate of reaction. The nitrogen dioxide gas we've seen is a brown gas. We've collected some of that into a syringe. The reason for that is being a gas system, we can actually have a look at the effect of pressure on an equilibrium. So if we have a look at the reaction, we can see that on the left hand side we've got 2 moles of gas particles, and on the right hand side we've only got 1 mole of gas particles. Gases at any given temperature and pressure occupy the same amount of space, no matter what the gas is. So you would expect the NO2 to take up more space than the N2O4, because there's 2 moles of it. So the left hand side of the reaction takes up more space than the right hand side of the reaction. Does that make sense? There's fewer particles on the right hand side, so they need less space. One of these reactions, the forward reaction or the reverse, I'm not going to say which one yet, is exothermic, so it gives off heat energy. The other reaction, the reverse reaction, is endothermic, so it absorbs the heat energy. So what I've got here is some iced water, tap water, and this water is about 80 degrees Celsius at the moment, so very hot. I can use the behaviour of this equilibrium in different temperatures to determine which one is the exothermic reaction and which one is the endothermic. So that's one of the conclusions we're going to get to today. The nice thing is, NO2 is brown, N2O4 is colourless. So the browner this gets, the more NO2 is being made. Which reaction is that, forward or reverse? Reverse, good. So favour the reverse reaction if it goes dark. If it goes lighter, it's favouring the forward reaction because that NO2 is being combined to become N2O4, which is colourless. So that's the background. Okay, the first one I'm going to do is I'm going to change pressure. Now, what we're going to observe is if I increase pressure, I'm putting the particles closer together. So initially it will get darker anyway because the concentration increases. So what we want to do is make the change, hold it there, and see if it fades or gets even darker. Alright? So, is that in my field of view there, guys? Okay, so sort of got a benchmark using the white in the background to see what colour it is. Remember, I'll push it in, which will increase concentration, so initially it will get darker anyway. But then I'm going to hold it there and we'll see if there's any change. Oh, I'm going to tighten that a bit, so it's not so good. Okay. So of course it's got a bit darker, and then while I'm holding it, you guys that can see the screen can probably see it better. What's happened to it? It started to do what? Do it again. Just let it reset. So I push it in and the concentration increases, so it gets a lot darker, and then as I hold it, can you see what happened there? Okay, what happened after it got darker? It started to go lighter again, didn't it? Okay, for you guys that are watching there, I'll just do it out here. Okay, so push in, it's darker, you see it starts to fade immediately, and I held it in place, alright? So that means increasing pressure has favoured which reaction? Make what? What's it making more of? N2O4, okay? Because once I held it in place at higher pressure, it started to fade in colour a little bit until it created a new equilibrium position, which had more N2O4. Okay, so therefore if I reduce the pressure, so pull out on my syringe, what would we predict is going to happen first? It goes clearer because of the lower concentration. And then while I hold it out there, what would we expect to see? Goes dark. Let's see if we're right. Oh, very subtle. It's not much, is it? Could you guys see a change there? Not really, eh? Okay, so that was our prediction. I don't reckon it's very observable, to be honest. It is what's happening. Yeah, very good. So I pull it out, it's lighter, and then only a tad darker, eh? Okay, so the pressure one's very hard to show. What What's a lot easier to show, now for this I'm going to have to hold the pressure the same, so I'm not allowed to let the syringe move. And I'm going to put it into different temperatures. So I'm going to start by putting it in tap water because that can be my benchmark, that's my control. So I'm just going to let it work out a colour it's going to go, and pressure. Okay, it's pretty good, that's probably enough. Would you like me to put it in iced water or hot water first? Hot. Yep, you guys all good with that? Rightio, so I'm going to hold the syringe in position so that pressure isn't a variable. Because we expect in hot water particles spread out and it'll push against me, won't it? So I've got to stop that happening. Sorry, it says we've got to do this thing. We think it's darker or lighter? Darker, okay? So it's got darker by having heat energy added. Adding heat energy is favouring the endothermic reaction. By making something hotter, I'm favouring the endothermic reaction. Got darker, so there's more NO2 in there, so the production of NO2, this reverse reaction must be endothermic. If I put it into ice, sorry, back to our control, if I put it into ice, we therefore would expect it to do what? Lighter or darker? Lighter. Again, you're going to have to hold the syringe because getting colder, the particles get closer together, so it's going to try and pull the syringe in. I don't want that to be a variable. Shot there. It's a bit lighter than it was. Right, not a lot lighter because our cold water on this not so warm day is probably only about 12 to 13 degrees Celsius. So probably only change the temperature by about 12 degrees. It's not a large amount. I'm going to leave that in there for just a little while to see what happens. It's ice out. That's going to make the pressure change as well, that's okay. So we can look at changing the system a little bit and see what effect it has on an observable change like colour. Link that to our chemical equation, and that allows us to work out which direction is exothermic, which direction is endothermic, and we can justify those colour changes based on, for example, the number of gaseous particles, the pressure one. But we also saw that by changing, if we change the concentration of something, we can also change the system. If I pump more nitrogen dioxide in there, it will initially go darker, nitrogen dioxide brown, but then if I close the system again, it will fade again. Because by increasing the concentration of a reagent, the system, to get back into an equilibrium, will make more of the product. So I'll go back to the original colour. There we go, that's better. That's a bit more of an obvious lighter colour. Okay. Now there's a question, sorry. Right, is equilibrium only for gas? No, it's not. So it's for all states of matter. So solid, liquid, aqueous, which means dissolved water, and for gas. Pressure only works with gases though, nothing else, because fluids and solids, so